Hello guys, I'm sure you're doing awesome. So this is the third installment of the database internals where we are going to further deep dive into two more acid properties, that is consistency and durability. So let's understand what consistency is. So consistency, like if I have to define it a little informally, it is something that like developer define based on what business wants. Okay, so this is again not a formal definition. Formal definition would probably take into some other route, but I wanted to make it really raw for the understanding. So, for example, there is a certain database state that must always satisfy few user-defined rule like constraints, invariants, referential integrity, etc. So, if you are not exactly a beginner into the database, you might already have come across these terms. If not, then few of them we will try to cover over here. So, suppose there is a bank transfer is going on, okay, between two customers. So, from customer one, uh, the custom the money is being deducted, right? And it is to be like to be a successful transaction, it is to be taken into the customer two. So, the total money of the system will be wrong if the money is being debited from the customer A but never credits into customer B. Okay, and it would lead to some kind of a logical inconsistency, and money will be lost in the thin air. And this is kind of a permanent violation of the business rule. So, unless repaired externally, like how can we repair externally? There are things like reconciliation processes. Okay, so reconciliation process means like suppose you have lost some money under cyber attack, and that is you go to your bank and you make a police complaint, and then in some way they try to make the adjustment, and they try to deduct the money of the person who took out your money, and they try to give that money back to you, right? So this is exactly what the reconciliation looks like, but our aim on a system would be always not to go towards reconciliation. So just to explain what referential integrity is, let's take this example. Suppose I have two customer here, like customer one and customer two. One is Alice and the Bob, or the customer A or B, and this is exactly what their account details are. Okay, so we have two basic tables where we have the customer ID, customer name, and probably have other information like customer phone number, address. I didn't want to make it such big, but just understand over here that customers information is handled in this table. Okay, all the customers informations are in this table, and all the account related to that customer are being handled in this accounts table. And how they are related, like if you see the customer one, okay, so for example, if you see this customer one, this customer one is also being referenced into this. Okay, so over here, uh, like any any customer that can be referenced from here, and all the customer details can be found in the main customer table. And what exactly is the account balance, or the account balance rule that is being set up if from Alice to Bob, like if we want to transfer money from Alice to Bob, that from the old balance from the account minus the amount. So this is a simple business rule, like the mm, old balance minus amount equal to new balance. Okay, this is true for Alice, like if the money is going from Alice to Bob, and from in the Bob's account, what is the deal? It will be balance plus amount equal to new balance, right? So the idea is, if you just sum it up, it should be always same as the previous sum which Alice and Bob had. Okay, so this is one of the referential integrity that you can see over here, that is being played. So now let's understand the consistency through a further more interesting problem. Okay, so suppose take the use case of Instagram like count. Okay, Instagram like count on posts and pictures. So what happens there? For the Instagram like count, suppose I have a kind of a aggregation table sort of a thing, like there there we are going to calculate the number of likes and we are going to store it, because on the fly if we keep on calculating it will be a like a every time there will be a select count start sort of a thing. So generally what happens is, like suppose we have a picture table and this is kind of a aggregation column. Okay, so what happens in the aggregation column? Like suppose in every 10 seconds, okay, in every 10 seconds, suppose I am updating the aggregation column. So if somebody likes my post, maybe in 10 seconds of time, I will automatically see the like count increasing. And if somebody dislikes, based on this cadence or that latency that is being introduced, we are going to see um, the like count is decreasing. So here the crux of this idea is like count is a denormalized field. It means to be the total number of rows and the likes in the picture ID. So we have a separate table itself for like. Okay, so here you can see this is a separate table. Earlier we have a picture ID, or it can be post ID, who is the owner of it. There is a blob reference, like probably in S3 or the Azure blob storage I am storing that particular photo and how many number of likes are there. And here we have the actual mapping of the number of likes. So suppose there is a user 200, what he does is he likes the picture ID 1. So over here, if you see, if suppose this is the exhaustive list of the likes, so here you will see for picture 1, for picture ID 1 rather, not picture 1, for picture ID 1, we see that there is two likes are there. Okay, so from the picture ID 1, I see there are two likes are there. So here if we try to do the calculation, we will see that there is no match is happening. So this is a kind of a problem in the referential integrity. Or there can be another referential integrity. Suppose I am having here customer 1, but for some reason here the customer ID got corrupted. Okay, your bank customer ID that you have, although it's a kind of a unique number, but suppose because of some of the error in the internal system, your customer ID got corrupted. So when you try to send the balance from one account to another, it will never be able to find your proper referential integrity, so it will not be successful. And here, as you can see, even for the denormalized field, there can be issues, right? So this table is, as we have mentioned over here, that this table is the source of truth for who liked what. Now, if we do a real-time validation, we see that there is a inconsistency, because although this is coming as 5, but the actual number is 2 likes. Okay, so this is a violation of referential integrity. Like, what are the violation? If cust1 is not present in accounts and vice versa, like customer ID is present in account but not in customers, so in that case the referential identity will be compromised. So this is one of the case. And also, as we saw here, for denormalized field, for denorm fields, suppose the aggregation or the calculation, doesn't match up, right? So in these cases we see that the referential integrity has been violated. So one more important case, what might happen over here is, suppose there is a picture, okay, this picture ID 1 that you see, and somehow I'm deleting this picture. Now if I delete this picture, still this referential integrity will be failed here. But the thing is that I'm not deleting the record from this table, right? Although I am deleting it from my pictures table, but here it still remains. So that means that they are, these are like orphan result, right? So we see that this kind of orphan result, like when we are not doing a proper database cleanup, this kind of orphan result may come up, and this sort of thing give the rise of the inconsistency around database. So eventually for the like count, as you see, this denormalization field is completely fine if the count doesn't matches the real-time number. What generally happens is we try to make it eventually consistent. Okay, so we will come about the different kind of consistency. So for bank account, as you can see, like if a transaction has to happen, it is must that the account or the customer ID present in the accounts is referred to a real customer which is being presented to customer. But here, if we see if we just see a Instagram post, like this Instagram post of Messi, right? So you can see it is being liked by so many people. Like so far, I don't really know the count. Probably more than 2 million people have liked that. So if there are like three or five here and there, do I really care? But eventually, like for example, somebody from the United States of America, they have liked this post. It might not come immediately because the approach that generally Instagram takes over there is it try to make it eventually consistent. So what happens is once this data for the like comes, it goes through uh, pipeline like Kafka, and the count may be slightly stale. Okay, so eventually consistent means like slightly stale in real time. So what happens is that the count may be slightly staled, but uh, that is like only for the read consistency. That might be a little bit here and there, but that is not at all any data corruption. This is intended behavior of the system, because it is not easy to count all the this kind of aggregation and all the likes in the real time, right? But you see over here with eventual consistency also the referential integrity is guarded. Why? So when a photo is deleted, the deletion event triggers the cleanup of likes and comments. So this is a very important aspect of system design, that when we are deleting any parent data. So suppose in case Messi deletes this photo from his account, then all these likes around this photo, like if I go to this likes table, it should fire up a or it should trigger a particular method which should clean up all this data. And again, it doesn't have to be real time, because for maybe 10 minutes or 15 minutes or maybe more, we can afford stale data. So over the time, to clean up our likes table, we can do things like that. But at the same case, if I tell you that if I remove one customer one, is it okay that if that customer is not removed from here? The thing is that here immediately it has to be there, because if there is any business rule that depend only on this account table, okay, suppose there is a certain business rule which is depending on this particular account table only, it is not even checking the customer. So in that case, if we are having the proper foreign key relationship defined, then it is totally fine, like it will give you a error. But at that very moment, the problem that would happen is like this if there is any stale data at all, that would cause a that might cause a disaster in the banking systems, because uh, this particular accounts might not even know that this customer is being deleted, and from the account there are some of the transactions keep on going on which will end up being a ghost or the phantom transactions, and again the money will be lost in the thin air. So to avoid this kind of scenario, the consistency that we need over here is known as strong consistency. Okay, so now two very important consistency related term that we came across so far. One is this eventual consistency when the Instagram like count is being concerned, and the other one is this strong consistency where this sort of a customer and the account or any kind of financial institute per se, okay, where the financial transactions are being are the subject. So in all those cases it has to be there. So let's take it a little bit more deeper way to understand what the strong consistency is. So I hope the eventual consistency is kind of clear. So for the strong consistency, what exactly happens, let's see that. Okay, so for strong consistency, if we suppose if we have a something like a Google Spanner. Google Spanner is a like Google uses their Google Spanner database. Okay, I will just write it, Google Spanner DB, for their global payments of ads. So Google, probably you are aware, like Google's highest revenues generally comes from the ads it places on their Google search. So this advertisement payments or the cloud billing, all these things that are happening, they use Google Spanner for that. So here there is no way the money can be double spent or vanish into the thin air, right? So if $100 is debited from advertiser, I will just write it for more clarity. If $100 debited from advertiser, it must appear on Google Ledger immediately, right? And plus it should be done exactly once. This is also a very important thing. Like if after making the payment again the user do some kind of a page refresh, then using the design principles like idempotency, we should make sure that this happens exactly once, because financial correctness is non-negotiable. Even like 0.00000 point 1% error would erode the complete Google revenue model. Okay, so that is why generally this kind of things are being maintained in a very strong manner and in a strong consistency, that if money is debited from the advertiser, unless the transaction only completes once it reflects into the Google's account or the Google ledger. Okay, so here two things we see, that there is a strong data consistency, and also another important thing is that here we are also need that read consistency as well. Now how exactly is read consistency differ from this financial cases and from eventual consistent places? So here if you see, uh, we are writing the likes in the real time, right? That we all agree. But what happens over here is this aggregation or the denormalization of those likes are not happening in a real time, maybe happening in a 10-second latency or a cadence time. So the data that we are reading, like when in Macy's post, the number of likes that we see, that might not be the real time one. But can we afford that thing in a system like Google payment ad platform? No. There the af- after the after the payment gets committed, it reflects on real time. Okay, so reads are served from the, like in this case, like there are the other concepts like leader replica and timestamp bound reads and the transaction timeout limits. Many things would come, but right now, just for understanding the consistency, this might not be like very much required for us. But another very interesting use case of read consistency is like if we are talking about something like a social media graph. Okay, so if you are aware that the graph databases or the graph nodes are the one which maintains the whole relationship across the globe for Facebook, like how uh, me or you, suppose we are both in each other's friend list, that's a bidirectional graph that is being maintained in the maintained by Facebook. So suppose I unfriend you, okay, and there are other databases which is preparing my feed, okay. So the case is like two friends are there, A and B. There is a there is a process which generates the post on my feed, okay, or on A's feed. Now suppose B has, so A definitely can see B's post, and suppose this is what a process one is, okay. Now this process one um, is generating the feed and doing all the stuff. In the meantime, B unfriend A. So A shouldn't be able to see B's content, right? But suppose this process is not even aware of the fact that B has unfriended A. So what would happen in that case? So maybe for that very moment the bees feed might come into the feed of or the bees post might come into the feed of A, but eventually like when the actual database sync happens, like in seconds later, like it doesn't take a lot of time because it is a graph database, but at that whisker of moment we might still be able to see the A's post, A might be able to see B's post, although B has unfriended A. Okay, because this process is not aware of the fact that this node is deleted. So in few seconds, maybe when like this process gets the updated data, then what would happen is it will see that the data that it will generate in that case, A in the A's feed, B's data won't come. Okay, so this is pretty much what like social scale, one of the little bit of read consistency staleness we can afford, like we have seen in this like count, or when your feed is being generated through the fan-in process, uh, you can see some stale data or some earlier data. Okay, so all these cases, like eventual consistency would come in play. Like one of the thing I have seen, like in suppose while using Amazon, if you are using it from web and mobile at the same time, and you are adding something in your cart, you can do this experiment as well. Something in your cart, it takes around 2 to 3 seconds, like even a single refresh doesn't bring the cart populated. It generally takes like 2 to 3 seconds to get added to, if you have added your the content in your card in web, then it takes like 1 second of time to sync, and similarly for the mobile it takes like 1 second of time to sync and getting reflected into web. So here also you can see like because it is in the cart and not like an immediate transaction is happening, so eventual consistency is there, but it happens with a very minimal time, like it doesn't take a lot of time. So although it is although these kind of things are kind of like eventually consistent, but we see that like the system are in a correct state over the time. So the bottom line is like what kind of consistency we are going to require, it is defined by the business and the engineers through the application design, or rather DB design, they enforce it. So I'm going back to my first statement that I did. Consistency is developer defined and based on what business wants. So if business doesn't need immediate refresh of that data, or user can afford some stale data, then we are going to do eventual consistency, weak consistency, whatnot. Okay, Now, which consistency model we are going to select? We are going to see all those consistency example in a little bit more deep dive now. So I've just created a very uh, basic box to understand what kind of consistency is useful when. So when there is a payment processing involved, invariably in all the system it has to be strong. So it has to be strong, right? That is the actual data consistency. And for the read also, we need a very, very strong read consistency as well. So the systems like Spanner, Aurora, or CockroachDB, they are very useful in that. Okay, so suppose user have done some kind of a profile update, like in your profile you have changed your password, and also you have changed your mobile phone number. What kind of consistency we will require if we still have the like if we have eventual consistency? The thing is that in that 3-4 seconds of time, it can be a very big security risk, like somebody else can try to change like your password in that meantime, and suppose they got hold of your phone by some means, so it will go to your old number, right? So this sort of things like the profile update, they also have to be a strong read and write consistency. So talking about like the normal RDBMS stuff, like the sharded MySQL and with sticky sessions, like we will always implement a sticky session sort of a thing, so that anywhere in the world, suppose be it in Brazil or be it in India, like in South America or in Asia Pacific, suppose you are opening the same page using the same uh, user ID, then you will see similar sort of settings. There has to be a immediate sync across the globe for that particular profile. uh, and for social media likes, we already discussed that we don't really need uh, like immediate consistency on that, and eventually they can be consistent. Now for recommendation engine, another important thing, recommendation engine, like uh, uh, Google is recommending some sort of a search result to you. You will always see that Google indexing, Google crawling, this kind of things are coming in play. So what happens is, like if I am just keeping my business open in my Google Map, it might not eventually come there. Okay, so what happens is, like that is also a eventual consistency, because like this sort of data are being indexed into Google's database, and then Google return it, right? So that indexing of this huge ecosystem that Google has takes some time. And like I have also tried to like give you some take example. Maybe you can do a little bit more deep dive into Kafka, Flink, and S3 using this, how we can create a recommendation engine that can be a very good system engine or a system design exercise for you. Now let's try to understand what durability is. So durability guarantees that once a transaction is being committed, if effects persist permanently into a non-volatile storage or in a persistent storage. So it guarantees once a transaction is committed, it is permanently stored in a persistent storage. Okay, like it can be a SSD, HDD. Generally, the database, when we are talking about databases, are being hosted into a Linux VM or something like that, right? So database is not a independent virtual machine sort of a thing. So the database is behind the scene storage, or the storage engine runs natively on the server that it is hosted on. Now to understand that, let's take this imagery. Okay, so suppose you have a PostgreSQL database in place, and this PostgreSQL database that you have, suppose it is being hosted into this particular VM. Okay, so this is, suppose it can be a Linux or Windows, any VM, and whatever the persistent storage the Postgres instance will use, that is basically this particular VM's storage memory. Now to understand it further, how durability happens, let's take one example and let's understand the use case, like where we might go wrong. So suppose the FedEx package tracking and the scan is happening, like when this kind of delivery consignment are being traveled in logistics from one destination to another, it goes through multiple delivery hubs, right? It goes through multiple hubs from one location to another. So in each of those locations, what the FedEx associate would do is they would scan, and probably in a, like, this is a simplistic table that I'm just thinking over here. This is kind of a table where the data will be stored, like with a scan ID, package ID, location code. So suppose just right after the scan, when the data is being committed, your VM, okay, this is your VM, and this get blasted. Okay, I'm just taking like an extreme example. This get blasted in some way, and in that case all of your data and everything will be lost, right? Suppose you were anyway making some sort of a replica earlier. So what would happen is, although this scan is actually committed, but because the data is blasted, so even the replica of the databases were not being framed, because database, as you can understand, like this is a IO operation, right? So when a data is saved onto the disk, it will come to the actual persistent stage. So writing something into the persistent memory is a IO operation. So IO operation is always expensive. In between that IO operation, the server have blasted, so I have lost that data. But ideally, through my log, I see that this data is committed. So what would happen in that case? So suppose this sort of a thing generally happens, like you are doing a insert into. So you can see there is a particular package ID I have given, and there is a certain location code MEM1. Okay. So after commit, even if the server explode, so this will show in transit to MEM1 MEM1 on restart. That is my aim. So what my aim is, if I restart my server, this database, whatever the data it had earlier, this should be able to reunite or reframe the whole data. Okay. So there is a very, very important concept which which comes in play to execute this, that is being known as WAL, or write ahead logging. So all the changes generally for this sort of transaction, what happens is, whenever any change is going to happen in the database, any delete, any update, any create, all the changes are first written into the sequence log. Okay, then they are applied to a database. So this sequence log is known as WAL, or write ahead logging. Okay, so I hope you understood the crux of it. So now, if I have a sequential log which have all the transaction that are being done into my database in a timely or in a ordered manner being replayed, so what I should do is, as a part of design processes, because uh, like taking a full database backup is difficult. So rather, if I just take a backup of this sequence log, okay, if I suppose keep a real-time backup of this sequence log in server 2 as well, like while this data is being committed, I am writing it to both server 1 and server 2. So what would happen is, during my database like during my server restart, okay, when the database is again being configured, I will just point that this has been my WAL, and from the WAL, please redo the transaction which we might have missed. So what would happen over there is, the full database, like this particular transaction, although seemingly it might be missed there, but with the replay, it will again come to the actual database system and it will be persisted. Okay. So not only these cases, just think of more sensitive cases, like when you click buy now in Amazon and you have like your order is already created and your payment is also authorized. But the moment that particular payment is being saved with a commit ID. For example, here your order is involved as well as your payment, right? So suppose your order related server or your payment related server or the microservices, as I can say, if anything goes down just after your payment is being authorized or just after your order is being placed but not persisting into the memory, so in that case AWS can use WAL to replay and restart to ensure that the order exists, that the payment is captured, the inventory is decremented, and any other things like with that log replay, right? So this is not only FedEx, like as we said, like in any e-commerce also, this is a very important concept. So this, what are the strategies to maintain durability? So that may widely vary. So as you can see, like durability is mostly should be a property of the server plus the databases. We generally do not like as developers, application developers, we generally do not deal a lot with those disaster recovery, but having those ideas will always help. So some system allow the tuning durability guarantees, like write to the memory now and I'm going to flush to the disk later. So generally what happens is like I'm going to put it into my RAM, okay, and from my RAM, we will discuss it in our later video. Like there is an in-memory buffer that are being maintained, and from the RAM into the actual disk memory, we are going to save later. Okay, in a later point of time, we are going to flush it. So we are going to keep writing into a RAM, and by the time it reaches to a certain threshold, we are going to flush it to the disk. So this sort of many optimizations are being done for increasing the throughput. But please understand, the moment we are writing something into the RAM, it is a part of a volatile memory, right? So this would always help us in the throughput, because if you are only running into the RAM, we are saving our time onto the IO. Later, through a batch sort of a thing, we can write into the disk and we can save a lot of time for us, right? So this sacrifices like strict asset durability for performance, and many log analytics platform does that. Like if you see the IoT or the telemetry, like Uber collects like actual real-time GPS pings. So if you really think that for like a straight 5 seconds, if some datas are not being saved into the database, will it be big of a problem in terms of like giving the correct location? For example, take Bangalore traffic. Okay, forget about 5 seconds, in 5 minutes also, like if it is stuck into the silk board signal, it will not go anywhere, right? So uh, like each ping that Uber does in this case, like the latitude, longitude, or the speed, is these are not mission critical data. So for non mission critical data, like as we said, like the Uber location updates, okay, like Uber location update, we can compromise on the durability for some seconds, right? So only because in our case only the latest location would matter. We would not really want to trace back all the path for all the single seconds that the vehicle was there. So in 2 or 3 minutes, how much the vehicle would change the road, right? So Uber collects this real-time GPS pings from the millions of drivers, and as we talked, there is like a losing a few seconds of data or a crash here is acceptable, okay. Same for the clickstream data. So what exactly clickstream data is, like suppose like my cursor is now going over there. Now if Xcali draw have clickstream deployed, then what would happen is Xcali draw will be able to see that there is a particular session that being generated, and these are the areas which were the most used. For example, we hardly go to these corners, right? In while working with the while working with anything like this, any notepad or the whiteboarding application like this, but our main application area will be our uh, point of concern. So the clickstream data will see some sort of a heat map here. So even in the clickstream, we can lose few seconds of data. So this sort of data, like where the billions of pings per day is happening, so there this sort of a strict Fsync or a very frequent batch or flush is not required. Okay, so you can see here durability, like on a very high level, if you see, you might see that the durability is being compromised, but it is being compromised for high throughput. Now this thing over here, when it happens, couple of time I mentioned it, this is known as Fsync. Okay, so Fsync is a very interesting thing. Okay, so what happens during the Fsync? Let's try to, we are going to try to understand through a very layered breakdown. So here you see, once the application issues a commit, this is a very important point to understand. Fsync starts working after this. So we are talking about Fsync right now. This Fsync, how it works, we are trying to understand that. So here, application issues a commit. The database engine, what it does is it append the transaction changes to the WAL buffer or in memory, and it calls the Fsync. So right now you see only our write ahead log buffer is there, and on top of that, that Fsync is being called. This is a very important point to understand, guys. And on Fsync, the WAL file is being written onto our persistent data storage. So when this operating system sees that Fsync, it forces the dirty pages out of the page cache and issues the IO and the SSD disk. So when a certain commit happens, okay, so when a certain commit happens, after that there is also a little bit of time, okay, a time period between commit and Fsync. So Fsync is definitely a OS based command, okay. So what it does is, whatever the things that are in memory, it takes it from there, and there are some other fundamentals of the dirty pages which we will just see in our subsequent video. So all those datas are being then persisted into the IO or the SSD disk. So when like Fsync is being used, you understand now how you can change that. So this is a completely like a very risky setting to play with, but you can, like, once you install your Postgres via database settings, you can play around with it. And generally there are things like WAL sync method using which you can generally work with this timing. So this is the final sequence diagram, guys. Here you see that the client has issued a commit, but that commit is not a immediate save into the storage. Okay, so what happens over here is this commit appends the changes into the WAL buffer that is in the memory, and then it will write the WAL buffer into the OS page. Then the Fsync is being called, and then with the dirty pages are being written into our storage device, and then we get the actual acknowledgement that my commit has been pushed onto my storage layer. So this is the point that I'm trying to make, like, although a very minuscule, but there is always a time period between the commit and the Fsync where the database also can go totally disarrayed, right? But at that point of time, if my WAL is being maintained, the advantage is, like, that if the replica of the WAL is being maintained, as I have mentioned here, like with the sequential log, then I can always build my database from those transactions by replaying those transaction logs, right? So that's the video, guys. Here we have covered the properties of consistency and durability. So now with this third video, we are done with the ACID property. In our next video, we will go real deep down into this level, like when we are flushing something into disk, or when we are actually writing a query, what is happening behind the scene with the database query planner, with the database query engine, or the disk. We will go into all the detail. So see you in my next video. Till then, stay awesome. Bye.